for inviting me. This has been a really great conference so far, and hopefully I can live up to the standard of talks. I'm talking about Eilenberg swindle. So first I want to talk about what an Eilenberg swindle is. And to begin with, I want to talk about what a swindle is. And a swindle is a cheap trick. And here is what I mean. So claim, so if A is a projective R module, then there exists a free module F such that A plus F is isomorphic to F. The way that you prove this is fairly straightforward. So because A is projective, it's a direct summand of a free module. So there exists a B such that A plus B is free. And now I'm just going to say, okay, well, I'm going to define F to be B plus A plus B plus A plus B. And, you can see how to keep going. And you go on forever. And now A plus F, well, you can parenthesize it in one way to get A plus B plus A plus B, and so on and so forth. And then, but F is also isomorphic to, it's isomorphic to B plus A plus B plus A, and so on and so forth. And these two are isomorphic for sort of dumb reasons. And this is the classic Eilenberg swindle, also sometimes called the Maser swindle or the Eilenberg-Maser swindle, in case you want to share credit. But in topology, it's usually called an Eilenberg swindle, so that's the name I'm sticking with. And you look at me like, that's a cheap trick. I thought you were going to teach me something cool. And instead, it's this cheap trick, and that's what makes it a swindle. Now, these days, when people bring up Eilenberg swindles, it's often in the context of algebraic K-theory. And algebraic K-theory says, okay, we want to study classically rings, and we want to do this by constructing invariants of rings that are computable. And this is the place where people sometimes laugh if you know a lot about K-theory, because K-theory is not computable at all. But at the beginning, it looks like it ought to be computable. And it does have very important invariants. So what is algebraic K-theory? This is going to be a 5-minute crash course on algebraic K-theory. So bear with me. Okay, so we want to study rings. And I'm going to say that R is commutative with unit. You can do it for more complicated things, but that just gets into way more complicated things. So we have R is commutative with unit, and we think, okay, what are invariants of these? And we think, R modules, we should be able to study them using R modules. And we can define a group called K0 of R. And this is the free abelian group. I'm going to say this incorrectly. If you know the correct answer, don't correct me, please. I will correct myself in a second. Also, warning to everybody, I'm about to lie, like Matt. It's a free abelian group on R modules, modulo the relation that A plus B is isomorphic to A plus B. So we're just looking at how modules decompose and assemble. And the reason I put these two on the same board is, looking at this, you should be able to say, no, wait a second, that group is really boring. Because, well, if A is projective, we just found out there's a free module such that A plus F equals F, which means that in this group, A is 0. So all projective modules are equal to 0 in this group. And in fact, for any module, you can take infinitely many copies of it and then add that to itself, and you get the same thing back. So you get the same kind of result for any module, and so you find out that this group is 0. And while 0 is an invariant, it's not a terribly useful one. Okay, so let's put in finitely generated. And this is actually a perfectly reasonable. Yes. As I said, please don't correct me, I will get there. This is a perfectly valid invariant, and it is interesting. It's often, because things don't often split, you really want exact sequences here. But this is called G theory. It is an invariant, it is interesting, but historically and for other applications, it turns out that it's more interesting if you also put in projective here. So I guess we're putting these adjectives here. And then this is the correct definition of K0. And it is actually already a useful invariant for rings. So for instance, if R is a number ring, then K0 of R is Z plus the class group. So it is already an interesting invariant, but it's not that interesting because it's very easy to compute often, which means that, you know, how sensitive can it be? And in particular, you can see that for any field, it's always going to be Z. So we can't even tell apart a finite field from an infinite field. It's just always Z. So it's not a terribly sensitive invariant. It can tell apart some things, but not in general. And in fact, before like general algebraic K-theory was invented, there's also definitions of K1 and K2, and I'm only going to tell you K1. So this is, you take the infinite invertible matrices, and this is the direct limit of GLN, which means that every matrix in here is really finite, padded with a bunch of ones along the diagonal to be infinite. So it's sort of, really, you can model this with finite, anything in here with a finite matrix as long, but you can make them bigger if you need it, and then you abelianize this. So in particular, yes, that's the definition. And so for instance, we see that there's a homomorphism called the determinant from this to R cross. And in many cases, for instance, for fields, this is an isomorphism. In many cases, this is not an isomorphism. But, you know, this is a good invariant. You can tell different fields apart. For instance, two finite fields, you can just tell it apart. This is going to be an isomorphism for fields. So you can tell them apart. This is, in fact, always injective. So, okay, great. How do we do this in general? Because given the notation, we have a K0 and a K1, and as topologists, we don't like finite sequences of things. We generally tend to think there should be an infinite one. So how do we define K of R, which I'm going to define as a space, but is traditionally actually defined as a spectrum these days? But you can define it in the following way. K0 of R is the Grothendieck group, so it's the group completion of pi 0 of the category of finitely generated projective R modules under direct sum. So finitely generated projective R modules form a symmetric monoidal category. We can take its connected components. That gives us a monoid under direct sum. And then we group complete this. And I'm going to say, okay, well, I have a 0 here and a 0 here. So I want to get rid of these and turn these into topological spaces. So I'm going to define K of R to be the group completion in a topological sense of the classifying space of finitely generated projective R modules, again, under direct sum. This becomes a topological monoid. There's a notion of group completion for topological monoids. And this gives us a space. And then we can define Ki of R to be pi I of K of R. And this definition actually works. This is a perfectly reasonable definition. You can't compute anything with it, but this is a perfectly reasonable definition. It has a bunch of good properties. This is a space / spectrum that a lot of people care about, and we really want to be able to compute with it, despite the fact that we can't. We really only know this completely for finite fields and a few other small examples. In general, we don't know what these groups are at all, and there's been some really cool computational results over the last few years about computing it for Z mod P to the N. That's a lot of really surprising and nifty results. And I don't think they've gotten a general formula, but they've used computers to do a bunch of these computations. And I think those results are very exciting. Okay, this is the end of the crash course on algebraic K-theory. This is what we are studying. We're trying to study this space. And often we'll generalize this. If you look at this formula, you can see, you know, I didn't really use anything here other than this is a symmetric monoidal category. So I could plug in any symmetric monoidal category. Actually, didn't even use that it's symmetric monoidal here, but anyway, you can plug in any symmetric monoidal category here in order to get this. Traditionally, I made a mistake here. I wanted to isomorphisms. But you can do this with other symmetric monoidal categories, not even necessarily symmetric monoidal groupoids. And this definition works. There's other generalizations. If you want to add in weak equivalences instead of isomorphisms, you can do other things. And there are other formalisms that let you get into computations of this. But again, it's hard. And so one of the things that we really want to do is at least be able to tell when it's zero. Is there a good conceptual reason when we can just say, oh, no, this is zero, no need to think about this particular example any further? And so one question, here, before I put in the amendments, it was very tempting to say, oh, look, nope, these are just going to be zero for Eilenberg-Swindle reasons. But as we all know, extending results on pi 0 to results about a space in general is very difficult. You need more information than just, yes, this space is connected. I think we would all be out of a job if every connected space were contractible. And so you really need a lot more data than just something on K0. And in fact, there is a version of an Eilenberg-Swindle that lets you get to the entire space, not to the spectrum. I'm actually going to give you two different versions of this. So the first one is Swindle number 1. And I'm going to give you the technical name and then ignore it. So this is Flask categories, which is usually only for exact categories, but you can use it for Waldhausen categories as well, for people who know what those terms are. If you don't, just ignore me. Okay, so suppose that we have a category C, which you can think of as symmetric monoidal if this is the only definition of K-theory you've seen, but this works for general definitions of K-theory as well. And suppose that we have a functor, infinity, from C to C, plus a natural isomorphism, or weak equivalence, if you like, from A plus infinity of A to infinity of A, So this is the identity plus infinity back to the identity. This is an isomorphism. Then the K-theory of C is contractible. And this is sort of a correct generalization of precisely this type of swindle. You have some way of creating an infinity like that F up there, and it's natural enough that all of the structure of the category is compatible with it. And because all of these constructions will also be compatible with it, you can contract everything out through the group completion. I'm not going to prove this. No, so this is there's a functor. This is infinity is a functor from C to C, just a functor, and a natural isomorphism from the identity plus infinity to infinity. Yeah, so I'll write this. So this is identity plus infinity to infinity. Oh, sorry. Yes, comma. I can do that if you like. So this is really just taking this, making it natural enough to work, and then contracting out the whole structure of the space. And when people say, and then this is zero by an Eilenberg-Swindle, a lot of the time they're pretending they mean this. But most of the time when you see this in use, the way it actually works, and the way I have been extremely guilty of using this is, we have this thing, but this is going to be contractible because we can construct this object F for any A, and so Eilenberg-Swindle, it's zero. And you notice that in this general flapping that I have done here, I didn't talk at all about the natural isomorphism. I just said it works on K0, flap, 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 yay. This is bad. No, just the natural isomorphism. That's all you need. Oh, sorry. The question is, does infinity need to be symmetric monoidal? And no, it doesn't. Actually, I don't think it does. I'm going to double check that, but I'm pretty sure it doesn't. Because no, you're right. It does need to be. No, okay, the question is, does it need to be symmetric monoidal? And you're right, it does, because the proof requires additivity. So yes, it does. So you're right, symmetric monoidal. Thank you. Okay, so most of the time when people are saying Eilenberg-Swindle, they're actually using, the question is, what does this imply to mean? I just mean it's a natural transformation, so it's a level 2 morphism, not a level 1 morphism. So often when people are saying they're using the Eilenberg-Swindle, they're actually using the second version. This one also works. No, you just, it's, I mean, it's an isomorphism. It's a natural isomorphism.
Oh, that's the name for that natural isomorphism.
What?
It doesn't have a name.
I didn't give it a name. It's just the natural transformation is a natural isomorphism. So it's an isomorphism. Okay, Swindle number 2 is, suppose that C has a multiplication in.
I'm still wrong.
Okay, yes.
Just say, what is the meaning of those symbols? Identity, both, sigma, and positive. Just say that in the sentence that
there's a natural transformation, which is a.
There is a natural transformation.
Yes, the double arrow is a natural transformation. It's a level 2 morphism in the 2 category of Waldhausen categories, not a level 1 morphism, which is why I drew it with a 2.
Level 2.
That's
what property?
It's an isomorphism. Okay, so Swindle number 2. Suppose that C also has a multiplication, meaning that it has a second monoidal structure. Which distributes nicely over addition. I'm not going to write down exactly what it means, but with tensor product works. So if K0 is 0, then K is contractible. This is just because if you have this additional multiplication, then your K theory is an E infinity spectrum. And if the K0 is 0, then the unit is 0, and so everything is 0. Most of the time that I have found when people claim to be using Swindle number 1, and I'm completely guilty of this, you're actually using Swindle number 2. You're saying, oh, well, we have this additional information of the multiplication, and so doing it on K0 is plenty. And this is great. I mean, this makes our lives a lot easier, and a lot of K theories actually have this extra multiplication. So for instance, for modules, you can do tensor product, and you have the multiplication, and it all works. And so these kinds of things work very well in many, many cases. This is a perfectly good version of the Swindle. And usually you're getting that K0 is 0 using something like that. So it all works and everything is fine. And this is really honestly an Eilenberg-Swindle. The problem comes when you want to use this, but you don't have the multiplication, and the flapping is covering a multitude of sins. And so I really want to give an example where this doesn't work, where your intuition will say, oh no, it's clearly 0, everything is fine, and you're just wrong. And so this is what I want to talk about. And first I'm going to pause before I talk about it. I'm going to talk about why I got interested in this kind of example. So I was working So this is joint with Reed Barton. So I was working on the following question. So if we look at varieties over some base field K, I don't really care about varieties, just pick your favorite model of what a variety is. It doesn't really matter. These are filtered by dimension. And you can, in fact, this induces a filtration on the cut and paste K theory of varieties. So we can do this K theory of varieties. And this has a filtration. And you can actually completely compute. This is compute the way I compute things, not actual computations. I apologize to all people who actually do computations. But we can actually say that if we take the filtered quotient, filtration quotients of this, so this is by dimension, we can identify this. This is the wedge product of the birational automorphism groups. So this is very bad word work. I apologize. So B sub n is the birational isomorphism classes of varieties of dimension n. So if you want the nth ones, you take all of the birational automorphism groups, and you want these as spectra. So you take the pointed suspension spectra of these classifying spaces of the automorphism groups, and that is what this filtration quotient is. So that's all you need. You don't need anything else. And we were playing around with tame topology. So tame topology is this idea that a lot of the difficulties that come up in topology come up because we let ourselves have any maps that are continuous rather than maps that have nice descriptions. So we're going to restrict ourselves to nicely descriptive maps. And then you get a bunch of results that are very similar. For instance, you can define every space has a dimension. Every space decomposes into cells in an appropriate way, in the same way that varieties decompose into irreducible components. And we wanted to know, is there a result like this for tame topology? And it is filtered by dimension, and this filtration does extend to the cut and paste K theory. And so the question became, is there a splitting like this or anything at all that looks like it? And the answer is, I don't know, possibly, maybe, we're still working on it. But an example that came up with it in it, when we were working on it, we ran into this swindle issue, because the answer was intuitively, clearly that it was going to be contractible. And we wrote down the proof, and we were like, we're missing a step in here somewhere. And then we spent a bunch of time thinking harder and trying to prove it's contractible and failing miserably until eventually Reed thought maybe it isn't contractible. And then it took him about 2 days to find a proof that it's not contractible. So I want to tell you about this example, partially because I think swindles are cool, and I also like when our intuition gets messed up by them, and also because I thought this example was very surprising. Yes?
I think there's only one birational equivalence class. So you can always find the projective space. Oh, birational.
Yes.
Oh, not degree.
Yeah.
Always correspondences to some degree.
No, we want birational isomorphisms. Yeah. Okay. So here's the example that I want to talk about. So we're going to define the following category. Our objects are intervals in the real line, and our morphisms are almost isomorphisms. By which I mean, so an almost isomorphism f from x to y is a map such that there exist finite sets S, which is a subset of X, and T, which is a subset of Y, such that F induces a map from X without S to Y without T, which is continuous, which is a homeomorphism. And putting a map, I really mean it's a map. It only really needs to be defined on this level. So, once you take out finitely many points, it's fine. It doesn't actually matter. You could define it however you like, which is why I don't really worry about it. And I don't want S and T to be specified as part of the data. I want it to be the case so you can take out more if you want, and it's the same map. But it's just if you take away finitely many points, you're fine. Everything is good. It's a homeomorphism. So F does not need to be continuous. F does not need to be well defined everywhere, but it's almost an isomorphism, up to measure zero things. And the nice thing about intervals in R is that the measure zero things, if you're working finitely enough, which we are because it's K-theory, it's just finite sets. And we're going to put a monoidal structure on it, which is just put two intervals side by side. I want to point out, I didn't tell you whether they were closed or open, and we're not usually comfortable with saying, oh, I'm going to overlap these 2 points on the endpoints, but it doesn't matter because every closed interval is almost isomorphic to an open interval and vice versa. So you can take whichever models of these that you like, and it really doesn't matter. This, by the way, is the model of one-dimensional tame spaces when you've removed all the zero-dimensional tame spaces. So this is trying to compute the level 1 filtered quotient under tame topology. Now, I said that tame topology doesn't allow you to take any morphisms. You have to, so it's not just homeomorphisms. You want to be able to limit yourselves to ones that you can describe well. So for instance, you could say piecewise linear. So which homeomorphisms are we allowed? There's two completely reasonable choices that you could make. One is the piecewise linear, and one is semi-algebraic. So semi-algebraic means you can write them in terms of polynomials and inverses of polynomials and really rational power series and things like that that are nicely defined. Piecewise linear, I'm going to guess we all know. I need to cheat because I will forget somebody's name otherwise, and then I'll feel terrible. If you choose this version, it is actually contractible in this case. And this is, Sandra, please tell me if I missed someone's name. In this case, it is contractible. So if you take the K-theory of this symmetric monoidal category, and the only homeomorphisms you allow are the piecewise linear ones, the K-theory is contractible. But in the semi-algebraic case, it isn't. So how do we know this? So the rest of this talk is going to be me trying to convince you that this is true. Okay, so why did I say that my intuition said, of course, this is going to be contractible? Well, if we look at Swindle number 1, we don't have a second monoidal structure, because if you wanted a second monoidal structure, you'd really want two-dimensional things, and we're only allowing the one-dimensional thing. So no second monoidal structure. So we're not in Swindle number 2 territory. We're in Swindle number 1 territory. And the infinity functor you want to take is the identity. So the claim is that A plus A is isomorphic to A. And this is fairly clear. You have an interval, and then you add it to itself. And then there's an isomorphism back to the interval just by shrinking it in half. That's a perfectly reasonable either piecewise linear or semi-algebraic homeomorphism. So A plus A is absolutely isomorphic to A. And so this is, so K0 is 0. And then you start thinking, well, in higher dimensions, it's got to work, right? Because, you're contracting all the maps, and it's, double anything is going to be the same as itself. So it's got to be a 0 also. And this is where I'm talking about the massive flapping, because this is the place where it fails. Because there isn't this natural isomorphism there. You can try to put it together, but that part even fails in the semi-algebraic case. This is a strong, much... in the piecewise linear case, it's a lot more work to prove it in the piecewise linear case than just using a Swindle. Because if you think about it, for this to be natural, you would need it to be the case that if you took you took any map from A to itself, and you put it next to itself, and then you shrank it in half, you'd better get the same map back. That's what it would mean for this to be natural. And while for just a linear automorphism, this is true because there's only one of those. Once it's piecewise linear, it doesn't have to be true at all. If you draw the graph of the map, it could look like this the first time, and then it looks like this the second time. These are not the same graph, so they are not the same map. So it's just not true. But the raw intuition feels really strong. How could it possibly be that, oh, you add something to itself and you get this, you get something different back? So if we want to actually prove this, we need to talk about K1. Yes. It's an abelian group, so yes. Okay, so yes, I have K1 defined here for rings. In general, K1 is much more complicated, and in particular, what would K1 of this even be? There's a theorem in general about these kinds of combinatorial K-theories where you have sort of geometric objects that you're decomposing and reassembling, that in nice situations, so this is me and those people over there, says the following. I'm going to write this so that it's actually completely true, but don't worry about the technical bits. So if C is an assembler, then K1 of C has the following presentation. I'm going to put a nice assembler and then not worry about it further. So in particular, this applies. So we have, so the generators are pairs A tau, where tau is an automorphism of A. And the relations, there's two of them. And one of them says that A tau plus B sigma is equal to A plus B tau plus sigma. You can see this looks a lot like the relation for K0. And then the second one is A tau plus A sigma is A sigma tau, or tau sigma. I'm going to write both. It doesn't matter because they're going to be equal because it's an abelian group. So you can see in the case of our modules, we had the abelianizations of GL, and you can see that that relation coming into here. This is not actually an example of an assembler, but it's an example where this kind of relation appears otherwise. So this is going to be an abelian group under these relations. And for instance, you can apply this to check just explicitly by hand that K1 of finite sets is Z mod 2, as it should be, because K of finite sets is the sphere spectrum and pi 1 of the sphere spectrum is Z mod 2. So this should be Z mod 2, but you can also just compute it from these generators and relations. Okay, so we have this tool, so now we can try to analyze K1 over there. And the theorem is that there exists a surjective homomorphism from K1 of that to the positive rationals under multiplication.
That is a semi-algebraic.
Yeah, this in the semi-algebraic case. So this is surjective. We conjecture that it's actually an isomorphism, but so far what we've been able to show is that it's a split surjection. So this does have a map back, but we do not know that this is an isomorphism. Yes, I'm about to say it. Okay, so the idea is this. Intervals contain generic points. So these are the 3 bullet points that I'm going to say. So the intervals contain generic points, not just the points of the interval, but every point of the interval is decorated with 2 generic points, namely what's happening above this interval and what's happening above this point and what's happening below this point. And because semi-algebraic sets things are nice enough, you can compare what's happening at these points. Automorphisms have well-defined degrees at generic points. And these degrees are 0 if the derivative is not 0 or infinity. I guess I'm going to put, yeah, I'll put 0. And I'm going to, I think it doesn't really matter which one.
Everywhere or somewhere?
At the point. No, I guess I'll put 1 because I want to put,
Generic point?
yeah, at the generic point. And it's Q not equal to 1 if the derivative, well, it's Q if the function is x to the q at that point. And it's the same on the positive and negative generic point if the function is C1 at that point. So I will not have time to prove this rigorously, but the idea is the following. Semi-algebraic function, if it's nice at a point, then it has a power series of rational exponents at that point. And so if the function is nicely C1, then the function is the same approaching the point from the top and approaching the point from the bottom. And this is that degree of the function is what it is at the generic point. And so you have a generic point sort of what's happening to the right of this point, and you have which is a function with some degree, and you have a function approaching the point from the bottom, assuming which is the function value at that point from the bottom. And then you say, okay, so if the function is C1, then the two approximations are the same. And if the function is not C1, or if the function is if the point is on the boundary of your interval, then you either don't have one of those generic points in your interval, so it doesn't matter, or the two functions are different. But you can only have finitely many such points where the function is different on both sides because it's a semi-algebraic function and they have these finite descriptions in terms of intervals on which it's these power series.
That's the map.
Yep, I'm about to write down the map. So we define this map, which I guess I'm going to call just the total degree from K1 to Q cross. And this is going to take a tau, and it's going to map it to the product over the x as a generic point in A of the degree at x. Actually, I'm going to write this slightly differently. To the direction. So what do I mean? So x is either equal to y plus or y minus, because it's either some point and then the stuff to the right of it, or some point and then stuff to the left of it. So the direction equals 1 if x equals y plus, and -1 if x equals y minus. So if we have a point y in A, which is in the interior, this means that both y plus and y minus are generic points of A. And if tau is C1 at y, then the degree at y plus equals the degree at y minus. And so their quotient, which will appear in here, is 1. And so most of this is just, they're coming in these pairs where they cancel out. Moreover, in fact, most of these are equal to 1 because, again, most of the time the derivative is not 0 or infinity if you have an automorphism. And so all of those are already equal to 1. Because if you're writing out a Taylor series somewhere where the derivative is not 0 or infinity, the first term is x. So in places where you're just sort of chugging along and your derivative is not 0 or infinity, this is going to be 1. And so we have this very infinite product, but most of the terms in it are equal to 1, so it might as well be a finite product. If the derivative at y is 0 or infinity, but the function is C1, these are going to cancel out as well. Because they come in these pairs. So those are not going to influence anything either. The only place that this gets influenced is really at these points that we've removed in order to make this a homeomorphism. And so then this product is going to be either the ratio between the degrees at sort of places where the function changes, or what's happening at the endpoints. And regardless, because of the way that semi-algebraic functions work, this is going to be a product of non-negative rational numbers. sorry, I forgot to put 0. They're going to be of positive rational numbers. And so this is well defined in this group. I'm not going to go through the proof that this is actually a well-defined homomorphism because it will take a long time and I need to develop the theory of generic points, and I only have 4 minutes really, and you don't want that and I don't want that, so we're not doing that. And to check that it's surjective, we just need to construct that section that I talked about, and that one is fairly easy because we know that 0, 1, x to the q maps to q because it's an automorphism of 0, 1. And nothing interesting is happening on the interior because of this argument that I gave you before. So we only need to worry about the endpoints. At 1, the derivative is non-zero, so there it's going to be 1 as well. So that part also doesn't count. So the only contributor is at the endpoint 0, which has no negative generic points because it's an endpoint. It has exactly 1 positive generic point, and at that point the function is x to the q because we defined it that way, so it maps to q. So it's surjective. This is actually also homomorphism that I'm guessing you can check. I'm going to ignore that because I mean it's function composition. Addition is function composition, so you multiply in order to compose functions. So the conjecture is that this is it. This is the only thing there is, that this is actually an isomorphism. But we don't know. That's actually, it seems to be a much harder result than either constructing this or checking that it's well defined. So, so we don't know. And I would love to discuss this with anybody. I would also love to discuss the more general question of what can we say about the K-theory of the stratification of K-theory, filtration of K-theory under tame topology, because I think there's got to be some really interesting stuff in there, but it turns out to be much harder to analyze than we thought. So we are working on it, but I would love to discuss it with anybody who's interested. And I'm going to stop there. Thank you very much for listening.